All right, we're going to look into spherical excess today through the arc of the parallel, the triangulation survey that they took back in the early 1900s. We're going to go through the data they took, the process that they went through to get it, some of the circumstances they were getting it in, and how they were interpreting what they were doing at the same time. And then we're going to go through some reciprocal zenith angle measurements. Talk today about the transcontinental triangulation and the American arc of the parallel. It's essentially back in early 1900s, right after the Royal Society had figured out the coordinates, spherical coordinates, and the geodesic coordinates, and all the coordinates they needed to manufacture globularity for the whole world. They set everyone out on this mission to map, to quote, map the world, even though they've had other maps with longitude systems and they're already going to adhere to the pre-existing coordinate system. They're going to map the world. The thing to note about this one, though, is it's the first time that they made corrections according to this new longitude lat system that they had installed. Seems odd that they would be so intent to send people out to use this measurement system to make sure that they adhere and make adjustments to the new spherical coordinate system. So before now, they would just go out and make the measurements, and they would jot down what they were measuring, and they would compute the angles, and they'd get the distance, and they'd tell everyone where where everything was. Now they're going to try and get that distance and try and force it into a spherical coordinate system with a bunch of excess. They're essentially going to take the flat measurements and convert them into a geoid. But let's see how they do that. And before we dive in to the American arc of the parallel, let's take a look at what we can expect to find from the basic steps of what they were trying to accomplish, right? So the fieldwork of the triangulation project is carried out with reconnaissance, correction of signals and towers, measurement of horizontal angles, dropping plumb bobs, perpendicular measurements, astronomical observations necessary to determine the true meridian and absolute position of the stations, measurement of the baseline, adjustment of the observed angles, I guess based on the last few things, computations of lengths of each side of the triangle, and finally, my favorite part, the computations of the latitude and longitude. I wonder why we would need that. Well, let's see what else we would need. I think we would do an intersection formula by what? Oh, look, intersection with the long lat system that we'll have to be correcting for. That's weird. I wonder why we'd have all this math here to do the exact line of latitude intersection with what we're measuring to try and get the correction to put in our logbook. That's strange. That can't be. Well, we'll look into that a little bit later, probably. I wonder if what we're going to be looking into takes into any presuppositions of any sort of Earth shape or geometric requirements. If we look at here, definitely geodetic datum, reference from which measurements are made. Okay, that sounds cool. Horizontal is known as a constant surface on which the positions of points can be precisely expressed. Because of their simplicity, ellipsoids are used as the basis for horizontal datums. Vertical datum is an additional vertical reference for expressing the elevation of points. It is based on a geoid or ellipsoid model. So it seems that they've already started by assuming an ellipsoid, and then, oh look, there's the geoid height, the ellipsoidal height, the ellipsoidal surface. So yeah, it looks like we're starting off on the right foot. And then we're trying to figure out what is geodesic surveying. And then if we look from Whitsett's debate, we learn that actually we must take into consider the true shape and dimensions of the Earth, a very rigid control for coordination of all other surveys. It is true that the Earth's dimensions must be known to enable the exact computation of positions. I mean, they have to already know, say, the radius or the rate at which it curves and the sphericity to compute where on their globular longitude and lat system they would have to correct to make it look like that. Jeez. The position is that geodetic surveys are carried out to establish rigid coordination of all other surveys based on computations on previously known values of the Earth's dimensions. So essentially, they have mathematically forged sphericity, and now they're going to go measure that sphericity using the same calculations. Let's see if that's what they're actually going to do. And we'll do that simply by adding up the measurements that they took. Right, so a quick tutorial on this. They're doing degrees, minutes, seconds. So what we do is, let's see, this one is 17, 46, 1883. I think I have it plugged in over here. 17, 46, 1883. So I have this all set up to do that. Plug it right in, you get 179.9841111. Don't know what the hell they're doing. Don't know what the hell they're measuring, but that's not curved. That's a flat measurement. That's weird. Weird, right? Turns out a lot of these are flat measurements. Matter of fact, there's a specific correlation with how big the triangle they're trying to measure and how much spherical excess they can manufacture. I mean, find. So when they say that they're measuring spherical excess, they're doing it in an amount that is measuring spherical excess in increments of 8 seconds. Just saying. Total of 24 seconds, you know. Excellent. Just a brief overview of the format here. First, we're going to go through the concepts. We're going to use McToon as the globe side. We're going to poke holes and present our side of the argument. We're going to thoroughly examine each of the holes McToon brings forth. Then we're going to go to the actual document itself. We're going to read it through for errors, corrections, refraction, things that we may need to poke holes in, and then we'll go from there. So I'm going to borrow a little bit from McToon when he did this debate with Whitsitt and Kai. I'm going to pull his little pieces of his intro when he went over spherical excess, and then we're going to attack everything that he says from there.
The surface of a sphere, a triangle always has more than 180 degrees. The surface of a plane, a triangle always has 180 degrees.
Let's try
exactly.
Out.
So if the Earth is flat, then any measured triangle, every one of them will be 180 degrees. And if the Earth is spherical, a sufficiently large triangle so that the measurement can resolve it, there will be more than 180 degrees in any triangle. So right there is just a little description of how it's done. It's called the amount over 180 degrees is called spherical excess. So if there's any spherical excess, then you know that the Earth is not flat. There was a survey. It was published in 1900. It's a 900-page survey. It's called the Transcontinental Triangulation of the American Arc of the Parallel. They used these theodolites. These are 20-inch long theodolites. Very, very precise. Better than 1 arc-second of precision in this. In order to cite them, they set up temporary housing, temporary viewing stations on mountaintops, especially across the Rockies.
Man, I had to stop it. I didn't realize that right there you said, if the Earth is flat. Look at the tool that they're actually using to denote over, let's see, 10,000 miles, 11,000 miles. This says that uses survey targets of ranges of over 100 miles. Okay, distance of 192 miles. Limited to use on sunny days and was further limited in regions of hot temperatures to mornings and afternoons when atmospheric aberration least affected the instruments and man lines of sight. Sounds like it's heavily optics induced. It would be heavily susceptible to refraction and atmospheric lensing and all sorts of things heavy down at the atmospheric side. So not sure that this is the best tool to denote a 10,000 mile triangle that has a spherical excess of 4 arc seconds. Just saying. Looks like it would be highly susceptible, actually. Flasher, and it would employ a second mirror. So this is 192 is the most they've ever used it at.
But it does not affect horizontal measurements. So they go over that in the book, and the way that you do get variations due to potential atmospheric effects dealt with is you take lots of measurements, lots and lots of measurements. They take huge numbers of measurements. They get a really tight standard deviation so that they know that the measurements are very accurate.
Values derived from lines similarly situated. Oh yeah? So they're doing all the work, are they? Nope. Here's the calculation for when we assumed all the values. Okay. Well, they're doing something. Resulting in differences of height from one zenith distance and from reciprocal. So then, I see. So they just take one example, mathematically derive it out, and say we did it. They go back and forth between each observation site. I mean, that makes sense to me, absolutely. They're just making lines of observations anywhere they can. This is an entirely optics-driven evaluation here. So here's the lines on the map. Here's where they were going, on top of the mountains. Lines of sight all the way through, trying to make sure that they keep it consistent. But man, when you're dealing with a threshold of a couple of arc seconds in just a tiny, minute area, then, you know, I feel like if one of these guys farts, or a frog lands on the, a butterfly lands on the lens, or the wind blows the wrong way, one of these markers is going to get skewed, and then you've lost your accuracy threshold, right? That's what happens when it's so narrow, so narrow a threshold to determine sphericity when you're trying to adhere to a predefined spherical coordinate system. This looks like the entire triangulation mesh. So they were doing a triangulation in an area where they'd never been done before, apparently, except here's this old map with all the old triangulation data in the shell architecture there for them to use. I'm sure they didn't use it though and operate it on the honor system or something. Let's see here. Wow, yeah, no, it's continuous.
Somebody using a heliotrope, you can see there's a telescope on it so that they can view the person with the theodolite who is measuring the angles.
For the first time, corrections have been introduced for the variations of latitude, as we said before. So, marks an epoch in the annals of the Geodetic Society. No kidding. Historic events in the progress of geodesy. So, now we're going to adhere to our old... Oh, look. And we're going to use refraction and these giant foggy observations. My God. Look at these things. Yeah. Oh, yeah, no, here's the crew. Here's the crew measuring optics to the specificity required for a couple gradations.
Globular legends right there, Griff. Those are your boys.
Tell you what you're dealing with. Here's the instruments they use to do it. You know, the more I look at it, the more firm and the more firmly I believe this, the more confident I feel that this is the truth. Right? These guys nailed it, man. Absolutely. Yep. I mean, specificity, the margin of error with a 1 arc second. But this guy, no. I would trust my life to him in measuring arc seconds. Look at him. He means business, right? These people set up this whole station and that optic to determine by line of sight that actually Earth is curved because we matched it to the spherical coordinate system we were supplied, guys. It's totally in the back. Listen, I may sound facetious, but I'm going through the historicity of this. This is really what happened, right? These pictures, they're real. They're from the actual event. Here's what we're really dealing with. When McToon says they built, you know, mountain societies and and structures, it's like, well, they took some monkeys up in some donkeys up in the mountains and they put some stones in a circle and then they built their structure there. It took some readings. I mean, you know, call it what it is. But again, when we're dealing with margin of error so tiny and spherical excess so small over small distances like this, I mean, I want to see some accuracy, some specificity, some professionalism. I want to see the markers on the side of the optics that we're using. I want to make sure that you're not, you know, messing up my measurement and you're doing it with the highest degree of professionalism possible. These guys, man, I mean, this looks like this was just thrown here to make it look like this was done to me. Back in the foggy mountains where no optics can see. And we're going to use this device, which can only see 192 miles, to detect a flash of about 8,000 miles through this foggy terrain. It's probably no problem. But you know what? He definitely saw it, and because he saw it, we know how far it is, and because we know how far it is, we know how curved it is. Absolutely, that guy's a hero. The coast. Yeah, the coast must have been difficult. Well, again, not with the hat, you know. Honestly, until looking at these pictures, I would have thought this was done. I would approach this with a different mentality than I am right now. This looks like an absolute joke. The tools that they're using and the instruments they have would not let them determine with any degree of certainty or specificity any sort of shape of the Earth. All they did was make repeated corrections to a predetermined spherical coordinate system, to the predetermined long lat system, to the sky, to the astronomical alignment, literally to everything. So they're saying they're determining the long lat, but they're aligning it to every spherical coordinate system they could possibly manage, including the celestial sphere. So when they say, look, behold, it matches the sphere, you got to say, yeah, but you laid it out like the sphere, you traced it like the sphere, you had the sphere outline, and then you colored it in like the sphere. So perhaps it was determined. I mean, this stuff right here, though, I don't know. Look at that. Look at the shack they built. This is a painting. This isn't even real. This is to illustrate and mark the event, I guess. Well, how did McToon describe these? Well, they are just magnificent. Absolutely magnificent. Oh my. The other thing is, if they're determining all these new long lat systems and they can't, you know, they have nothing else to base it on, why do all these old maps exist from previous 1875? Well determined with their own longitude lat systems. They have their own cubics. I mean, did this just come from nowhere? Are they guessing? If you're a betting man, you might say they might have used something like this as well to cheat, right? Line it up. If we want to make it adhere to this system, we have all the data to do so. Here's a couple more. Another composite. Looks like more long lat systems, more determinations. Definitely have a determined grid already. Not uncalled for. Oh, look, another one. Same time, well before the survey was conducted. I'm starting to see a pattern, guys. I don't know. I'm starting to see a pattern. I might suspect nefarious action if I didn't totally respect the integrity of these participants. And, of course, McToon. Since we're talking about, you know, optics and measurements and angular resolution and, you know, what they're supposing is Earth curve as they measure, you know, the ground receding away from them, let's just go through, you know, the actual explanation for why things disappear bottom up and the limits of angular resolution, the origins of the Rayleigh criterion, and how it affects what we're talking about, right? So the only diagram we need to know, this is how you see simple lines, planes, and a circle for good measure. See how it extends outward radially until the certain point, and you can look at what you see as an eye line, and so if we take a distance along the way is misjudged. He's going to go through just a brief description of angular resolution. I think he does a really good job.
I'm going to demonstrate how we can make an object disappear bottom up without the need of curvature, or without the need of a physical obstruction for that matter. Now you globers are going to sit at home and say that table is just higher than the observer height or the camera height. Now let's get that sorted quick smart. When we zoom in, we increase the focal length and increase the angular resolution, and we can resolve that coin in its entirety. As you can see, the bottom of the coin shining
I love this
when
example.
you zoom back out, the coin is unresolvable again. Nice flat table, no physical obstruction. This is all optical. There's absolutely no obstruction here. This is due to angular resolution. The angle from the observer to the coin was far too small to resolve the coin. Now when I lay it down, we can still see the coin flat on the table. No problem. And you can still see some table underneath the coin. But when you zoom out, the angular resolution is way too small to resolve that coin. Nothing to do with physical obstruction, and the table definitely isn't curving. A 100% of the light of that coin is still reaching the observer. The only thing that is creating this optical illusion of something disappearing bottom up is the angle to which you are viewing the object.
I like this one because he goes into the explanation a little bit, and it matches what we've
As you
been
can see,
saying.
the entire coin is resolved. And when you zoom out, decreasing the focal length, it's unresolved. Now, if this was a ship out in the water, all you globers would assert that it is Earth curve creating this bottom-up disappearance. But as I've just shown, angular resolution is a thing. this left-hand side, optics, the best focused spot of light that a perfect lens with a circular aperture can make is called the airy disk. Now, as you can see in this left-hand side, there are 2 points of light and 2 Aries disks. They are both resolved. Now, when they get closer together, this meets the Rayleigh criterion, or the diffraction limit. And so the Rayleigh criterion specifies the minimum separation between 2 light sources that may be resolved into each distinct object. And when the light sources get even closer on the right-hand side, they become unresolvable. So relating this to my observation, when the coin is closer to the camera, it is fully resolved. As you start moving the coin away from the camera, it meets the Rayleigh criterion, or the diffraction limit, and this creates a smaller angle, making the coin disappear bottom up. And when you move the coin further away, it becomes fully unresolved. Now, as I said, 100% of the light from that coin is still reaching the camera, it's just unresolved. But when you zoom back in, you increase the focal length and you increase the angle at what you are viewing that object. Now, when you zoom in enough, it will meet the Rayleigh criterion, where you can see the 2 distinct objects again, the coin and the table. And when you get past that diffraction limit, you can fully resolve the object. Now, this has all to do with the angle that you are viewing an object. Now that we know about angular resolution and the diffraction limit, let's add some distance. This pole is about 3 foot off the water, and I'm going to put my camera on top of it. Example, when you zoom out,
Same thing.
it reduces the focal length, and the angular size gets so small that it reaches the diffraction limit. When you zoom back in, increasing the focal length, the angular size increases, and you can resolve it again.
I think Mitchell did a really great job there explaining that. I think that's kind of the whole shebang. I think this right here.
I mean, I'm not going to claim that they're measuring like that with that margin of error, but if all the other things weren't true, if all the other corrections and applications still weren't applied, I would still argue that whatever drop in distance you're measuring would just be, the resolvability of your vision over the long distance, nothing to do with Earth curve. But we don't have to argue anything, fortunately, because it's super easy to destroy all of this.
It's kind of the clincher as well when you're looking at it. And if you read this one, it just goes over for information above my eye line, the descent rate is steeper, but you have less of an angular compression rate. So it essentially puts that you govern the bottom of your horizon because it's closer to where your eye level is, and that's why the bottom recedes first, essentially. So wherever the information above your eye line is, those 2 halves have to collapse, and that's what you see above your eye line. So the top continues on independently, but you will never see objects diminish in size, reach the theta top, and recede into the top because they have already set into your lower horizon, because your eye line sets the lower horizon as the closest border. The higher the ceiling, the steeper the descent rate within our perspective. So this is how the brain interprets it. If you look at this one right here, this is what we're talking about. It's essentially why things disappear bottom up. You have the Rayleigh criterion for what can be resolved, and then you have the disappearance of your angular resolution limit right about here, and this is how we interpret it, right? So this is kind of the whole argument, and then when they're trying to use theodolites to detect this, so-called curve and then interpret it optically back to the radius of the Earth because they're using a predetermined spherical coordinate lat long system. I mean, you can see there's tricks upon nested tricks all the way through. So this is what we're really talking about, and this, of course, is the real explanation. So now let's go on with the rest of the destruction of the survey. Seems a little crazy when even in the preface here, I think this is page 18. Yeah, has been completed. The valuable material has been supplied for a more exact determination of Earth's size and shape. So it's literally set out to determine the size and the shape, and they've been hampered and hamstringed and guided and supplied with replacement tables and coordinate systems. So I think I know which way they're going to end up. So this says improvement in the field methods has marked the base measures and triangulation and astronomical determinations. Progress of the work has kept pace with the progress of geodesy. They said, let's see, The ordinary formula for spherical axis must be extended to meet the demands of the great triangles from Pikes Peak to Sierra Nevada. The laws of refraction, applicable at lower and equal elevations, require modification with great inequalities exist in the heights of stations. You don't say. I mean, when you're taking measurements of 1,000 miles across based on optics and you're through a valley of fog? I mean, maybe. The calculation of geographical positions enters a new phase when lines of sight 182 miles long are to be dealt with. Remember, instrument they're using has never been used more than 182 miles absolute max. No, don't worry about it. That was totally accurate. The adjustment of the triangulation, that refined operation by means of which incongruous observations are made to blend harmoniously according to the mathematical theory of probabilities. Let's go back and read that again. Hold on. The adjustment of the triangulation, which is a refined operation by means of which incongruous observations, meaning ones that don't match, are made to blend harmoniously, meaning we'll make them fit, according to the mathematical theory of probabilities. We'll mathematically make it fit. Literally is what it says. Excellent. Assumes a greater significance in a chain of 2,600 miles of continuous geometrical figures. So, again, outlining here, their plan is to use this device, 182 miles sight long, optically, dependent, has never been used longer than that. We're going to string them together for, say, I don't know, 2,600 miles of varying lengths of terrain and elevation. We're going to depend on these instruments to end up with a measurement with including a degree of specificity of, 1 to 2 arc seconds. It's going to be easy and perfect. Here we go. Don't forget that, of course, they're going to be using corrections for the first time for the variations of latitude to adhere to our geodesic WGS84 spherical coordinate long lat system. So it's going to be great. Can't possibly go wrong. Definitely doing objective science here, fella. And the more stuff you read, the more you find. So in consequence of Earth's rotation, the vertical line at a place is slightly curved and is concave to the pole. The observed latitude, being the angle which the tangent to this curve makes with the plane of the equator, needs, therefore, to be referred to the foot point at sea level. This correction is always negative. So they're correcting for the altitude for Earth's motion and for all over latitude. Look at how many latitude-dependent corrections they give. All of them. The correction of a variation of a pole cannot be ignored. Corrections to azimuth with this difference. Probable observer error generally exceeds the effect. Sure. Oh, look, a shift of a pole of less of consequence. The corrections for latitude, azimuth, and longitude. Again, what are these correcting to? We saw in the beginning from our prediction. They're adhering in corrections to a spherical coordinate long lat system. Oh, no way. It's crazy. The coordinates from our prediction, instantaneous pole of rotation with reference to the average pole. So again, corrections to latitude, azimuth, and longitude. So what are they measuring? It looks like they're doing more correcting than measuring. The resulting corrections are quite reliable, as they depend directly upon the observation. So, observed latitude, your error rate, what you should correct it to, so that we can give you our correction for the spherical coordinate adjusted latitude. This is insane. The abstract of resulting azimuth. So literally everything is tied to the coordinate system. They correct way more than they measure. Continuously recorrecting back to the spherical coordinate system. So again, correct back here, correct back here. Oh look, correcting back to the stars and the ulnar ephemeris. Oh, variation of the pole. Got to correct all of our angles for that everywhere we took them. Again, this is the professional, absolute certainty degree of measure that these people want to go with. This is what McToon tells everyone, right? They may therefore be advantageously scrutinized in a general way before proceeding to the determination of the final corrections to our geodetic coordinates, meaning we're going to choose what we're going to make, which errors we're going to throw out, which margins we're going to adhere to, and at the very end, which coordinate system we adhere to. So, I mean, this is insane. If this is what's put forth as proof of the globe, man, I'm happy I made the right choice. Will you give the geodetic best suited for the whole triangulation? So they just pick it. They choose it all. And this one is a kicker, folks. In accordance to the principles laid down above, we derive the following values as correction to the preliminary latitude, rejecting all values greater than 8 minutes, using all tabular values 4 to G. So literally they give it this range to ensure that it, derives sphericity at the appropriate radius. If they didn't do this, the radius would be much too large. They'd have all wrong data. Insane. I think this is the second document we're going through. So, oh look, more corrections, latitude dependent. Definitely corrections, latitude dependent. Don't worry, we're measuring. We're not correcting to the spherical coordinate system, I promise. Don't worry about that. Oh, like just another correction for the variation of the pole. So if I understand this correctly, they're using a theodolite or a total station to look out at a point and using an optic and line it up and then assume that that downward drop is Earth curve. But if I line up a theodolite on something like this with a atmospheric disturbance moving, I'm not really sure where the hell I'm aiming, and I'm certainly not sure what the deviation will be, and I'm damn sure that whatever that is not resultant of Earth curve, right? If this is what they're measuring with a theodolite and reciprocal zenith angles, an optical forward drop, then I'm pretty sure the deviation they get can be prescribed to atmospheric changes like this well before any sort of Earth curve as a direct result of this deviation. As you can see, it changes and drops all over the place depending on the condition. So not really sure what the argument is. People can't possibly think that's Earth curve. All right, and that should do it for the American arc of the parallel and spherical excess. Hope we've thoroughly put this to bed with their ridiculous frequent adjustments to spheroidal longitude and latitude, and to the stars, and to any other coordinate system they can get their hands on to make sure that they end up as a geoid or a spheroid. Definitely have any questions on this, hit me up, and I'll be happy to answer them. And now we're going to go into a comparative topic, but different, reciprocal zenith angles. So here we go. Well, before we do that, what do you guys think about spherical excess and surveying and all the good first part here? Everyone but Ruhef.
Pretty insane. So the larger the triangle, they get away with computing in more excess. Did I gather that correctly?
Yes, sir. And also McTune has a nice aggregation of data where he made sure to point out that actually they would plan to expect more spherical excess with the bigger the triangle. Ruhef is typing to me right now. I bet that's what you're saying, Ruhef. I know. They retroactively put in this like a prediction. Well, actually, we know that we expect to get more the bigger it is. Obviously, we don't expect to find any in a small triangle. But it's equally true that you can't manufacture it in a small triangle either. You could easily manufacture it with a bigger triangle.
And so then they're using, in this particular situation, they're using heliotropes over distances of thousands of miles, so like order of magnitude further than they're ever meant to be used, correct?
No, not all at once. They're doing stages. So I think they're trying to keep more or less in the limit of each observation. Okay. But I'm not sure. I don't think they're going 8,000 miles. But they are using those things for a duration of 8,000 miles through various topography conditions.
But then you said they were at various altitudes, and so one of the questions I had about that is like, how do they even know the precision of the altitudes that they're at?
Well, Toby, they have some altitude corrections that they apply to make sure that when they're at that altitude, at that latitude, they're properly sighting it in according to the geoid or the spheroid, whichever model they ended up choosing.
So the uncertainty of their altitude actually allows for them to make more assumptions.
There you go.
Okay. Yeah. That angular resolution video was really awesome.
Yeah, Ruhef was blowing up because he likes to pick on the actual Rayleigh criterion being applied as a measurable sort of a warping effect. But in reality, the issue for us is like when Globers present those long distance pictures and they go, "Oh, this is Earth curve," it's because they never properly account for compression into the distance, literally resolvability limit, and then how it recedes into your lower horizon. They can never properly account for optics in a picture, and that's why they like to apply orthographic views and simple trigonometry and go, "Haha, behold Earth curve." But you can only ever find that pesky bastard in those mathematical equations, it seems.
Yeah, so that was actually, like, I was a little confused when you first brought up the angle drop thing, like of how that was. I thought we were done with Arc of the Parallel, then you went back to it, but then I understood at the end because so they're using a total station and they're looking out to a point, and then like what you show with the video of the coin is that there's a downward drop, there's diffraction, and there's like a diffraction limit, and then because of that, they're just assuming that downward drop that's necessary due to all optics and due to the convergence and the fact that we don't have an infinite resolution. Like, we can't just zoom in with our eyes or whatever infinitely. Like, we have a resolution from our fixed point of perspective. So they're taking that downward drop and calling it Earth curve. But it's just simple optics and angles. So, I mean, like, yeah, that was a really, really good demonstration. And I like curious how that even gets properly accounted for in their quote unquote measurements, you know?
It never does, right? Turns out. So, like, it's good to point out that if all the things that I found and pointed out weren't true, if there was no corrections, if there was no, a coordinate system, if there was no celestial sphere corrections, if there was no altitude corrections, if all of that was still there, like, I would still say whatever they managed to measure as drop over distance over those big distances would have been the same sort of resolvability limit that we have on flat Earth. Like, no big deal. They're saying that they drop over distance not only is how they see on the sphere, but that's how it is for reality. Therefore, they've made that exclusive to the globe, and they're like, "Haha, flat Earth, what do you have?" And it's like, no, it works. It works that way for us. You guys have reverse engineered and bogarted it, and then said that we have to come up with a new explanation. No, it drops from the bottom up. The distance you go away from it due to the resolvability of your eyes being able to see. And that's why you can bring it back when you bring a lens in and zoom in, because it increases the resolvability past your original limit. Super easy. But yeah, we won't have to do any of that or worry about it because there was a buttload of corrections. So many corrections that there's just pages and pages and pages of them. So when I first asked, you're not going to just correct the measurements to a spheroid system, like when I was on Troubling Tribune, and I asked him, he's like, no, that's ridiculous. We don't do that. I was like, oh, good, because that would be silly. And then I opened it, and it's fucking 30% those corrections, and I'm like, okay, all right, someone, okay. So yeah, anyone else I'm gonna put this American Arc of the Parallel to bed. We can all bring Spherical XS as revised, and we can cite mctoon.net/se as flat Earth proof whenever anyone gets smart.
Excellent presentation, man. Really, really answering the question, which came first, the geoid, the ellipsoid, the Clark model, so really getting to the bottom of this. Fantastic work, man.
Rock on to reciprocal Zennies, dude. RZAs. This has been such a hot topic in flat Earth. I hadn't actually heard anyone rebut it or argue it, really. So I went to Ruhif to see if he could supply me with a rebuttal, which he didn't. But we know that
he didn't debunk his worldview for you, bro.
Yeah, well, I asked him nicely. I was like, "Can you show me what I can do to make this look stupid?" And he was like, "I got you." No, the way that you bring it down isn't the way like you don't go through the process of the hypotheticals and dance around and nonsense. Then you have to attack it at the source. So we'll sort of apply the same method, and we'll see how we take that on.
Figure out if lines are parallel. Let's take these two dashed lines on either side of the screen. We can figure this out. We take a third line that intersects these two dashed lines. We measure the angles on one side of that line intersecting those two dashed lines. If angles A and B add up to 180 degrees, then those two dashed lines are parallel. If A and B add up to anything besides 180 degrees, then they're not parallel. Pretty simple stuff. Now let's apply that to a practical field exercise. We have an Occupy station at A, we have an Occupy station at B, and we're going to measure reciprocal zenith angles. The spherical expectation is that when we add A and B, those angles, those zenith angles will add up to more than 180 degrees, and then those plumb lines would not be parallel. We would know that. Okay, it doesn't matter if we have different elevations for points A and B. We're still going to measure zenith angles from A to B and then from B back to A. When we add those zenith angles, we expect that on the spherical Earth, they'll add up to greater than 180 degrees. So I've gone out and I've done that myself. I picked two random points that were 1,252 feet apart. That was a random distance. I wanted it to be at least 1,000 feet, and I just kept pacing a little bit more. Like, this looks good.
I like my favorite surveyor because he made more flat earthers than anyone that I've ever met. He made more flat earthers than anyone. He's the only one that I've ever seen talk about it, and it was the first one. So I thought it was good to have him do the example to show us how they're supposed to do it before we attack the foundation. Forget his name. He's gone from the internet now, but yay, main surveyor.
And I set my 2 points, 402 and 404, and I measured zenith angles, A and B there, from 402 to 404, and from 404 back to 402. I added those zenith angles together and came up with 180 degrees, 18 seconds. Hey, that's more than 180 degrees. That means that those two plumb lines are not parallel. And here's my actual field notes from that exercise. Now, anything worth doing once is worth doing 4 more times. So I went to another location 100 miles away, and I did the same procedure, measuring reciprocal zenith angles between 2 points in 4 times over 3 days. And these are my field notes from the first series of measurements. And over the course of those 3 days and those 4 series of measurements, the mean divergence of the plumb lines came out to be 16.2 seconds. Interesting enough, the National Geodetic Survey predicted 15.0 seconds of divergence. So not too shabby. We had a standard deviation of the mean of 1.4 seconds, more or less, plus or minus. And that means that the correct answer was contained within the margin of error of my final mean.
All right, so some general information taken from it. And it ends up not really mattering, but let's just take you through what he's doing here that makes him feel so superior. The math, because they always throw out numbers, you know, perform some calculations and pretty much wave their hands, abracadabra, there you go, the globe. I don't know. So, I mean, what he's doing here is he's taking an angle measurement, you know, arc, degrees, minutes, seconds. He's writing it down. He's taking the inverse from 360, writing that down, going to the next spot, taking the measurement, writing the inverse down, you know, all the way through these 5 measurements. And then at the end, he takes the average of these measurements, and then he takes that one as one. This is one reciprocal zenith angle on this side. And then he goes to the other side and starts taking the other angles at the other spot, and does the same process. So make a measurement, inverse from 360, write them both down, get the correction, right? So all of these, every single one, and then get the average. So in case we're curious, he would do something like this, right? So I think this is it, actually. I took all his data. Let's see. Yeah, so this one is this one, right? All the way through, get the minutes, get the seconds, parse it out, add them together, get the average of all the 5. So these are all added together. These are all the averages. And then finally, you have the average of the average, which is what he was doing. So that's one reciprocal zenith angle, and then you throw them together. So just some math, right? Just some math with some presuppositions, and the presuppositions are what gets you into trouble. It's never the actual computation. All right, so to provide the answer for reciprocal zenith angles, we consider what we just went through with the survey and spherical excess, and how they hid the you know, process of adding all the spherical excess data right into the process of adhering it to the spherical coordinate system, and you know, the large amounts of spherical excess only could be manufactured when they had enough room to do it within the mathematics of the formula. So turns out what they do for this is sort of the same. Essentially, it all boils down to how do they get this plumb line. They take these measurements, they make these determinations, they decide that they know based on this the whole shape of the world, and that we're wrong. Okay, well, let's take a look at what they're doing and how they're doing it and what they're claiming, right? So, so as it is, they don't use any sort of, you know, geodetic coordinate system to measure or build or plan. They do everything on the flat plane, right? They take flat measurements, they composite flat data, they stitch it into a geodal dimension, then they apply the fluctuation of the plumb, then they get their arc length. So, well, let's start with, you know, on a flat plane, the local plumb just drops down perpendicular. Then you have your, you know, your mark to the horizon, super easy. No extra horizons generated, no complications. On globe Earth, plumb is not plumb, right? It's down to the center of the Earth. And that's because on a globe, it's only relative to the center of mass, right? So there, you can see the problem beginning to expound quickly, right? We're trying to prove the shape of the Earth, right? That's the reason for this discussion and for this argument and for this example. And then we're already trying to prove the model by invoking aspects of the model almost immediately, right? So down to the center of the Earth. So we're assuming that it's down is only relative to the center of the mass. You can only determine the center of the mass that is a result of gravity due to axial rotation, right? Because you only have down because of that. You have to assume also there's a gravitational flux. So you have to assume gravity due to axial rotation, down is the center of mass, and then there's a gravitational flux. So we're already in 4 times presupposition land to explain the downward nature of your, baseline plumb bob from which you've measured to have me assume that we're going to prove the shape of the Earth from your measurement. Okay, so you have to presuppose the spherical nature pretty much of almost every aspect. You definitely have to know the exact radius, which is, kind of where we lose it. If you're presupposing a radius, we are pretty much out at this point, right? So you have to have it down to a high level of specificity to get the angle for the plumb bob, so not just a rough approximation, like I put a stick in the shadow, I know what it is. No. You need it down to the highest degree of specificity possible. So, and to be clear, they're assuming gravity is pulling us towards the center of the mass and down, and that's the nature of the axial rotation, which again presupposes the spherical nature of Earth, invoking, three aspects of the model that you're tending to prove. Just want to make sure we're clear along the way here. So use the angle. Use the radius to get the angle on each plumb, and then you get the arc length with that. And that's, different. It's a different than a line on a flat Earth. So again, if it was a flat Earth, we get a line. It's super easy. On globe Earth, you don't get a line, you get an arc. To get an arc, you need a radius. There's no other way to do it. You can't just plot a line, right? So again, geodetic surveying cannot be even accomplished or initiated without the radius model. We certainly can't verify it without the radius value. And therefore, logically cannot be used to prove the globe model at all. But the nature, by the way, the definition of a geoid really means that gravity potential is equal everywhere. And that means that the direction of gravity has to be perpendicular. It has to be that way because without a plane, you cannot make measurements that we're talking about that prove a plane and prove a globe, or you can't determine down without this. And even though the geoid says they can't. So they have to use the same thing that we do. Now, just to bring it all together here, we have a wonderful quote about the first deflection of the vertical, right? We were talking about the importance of the deflection of the vertical. That's how we got here in the first place, to think about what does that really mean? What does that plumb bob align to? And let's just think about...
Right, just so the deflection of the vertical is what they know about. This is kind of the process that they can't really tell if the plumb bob is totally level, so they have this geoidal horizon that intersects with the other horizon, and then there's this deflection zone where they're to a certain degree are unsure of the measurement. Actually, in the American arc of the parallel, this held them up quite a bit. They had a bunch of this, and because of it, they didn't trust their measurements for a good portion, and they were all kind of messed up because if you think you're on a sphere and you can't find level, you're a little bit unsure of those reciprocal zenith angles that you're trying to differentiate to show that it's actually parallel. But we'll continue.
It changes, the deflection of the vertical changes with position along the curved plumb line. Therefore, the deflection of the vertical at the geoid does not necessarily equal that at the Earth's surface, and vice versa. This is the nature of the problem. In order to equate these two quantities, the curvature of the plumb line between the geoid and the Earth's surface is required. This is the part, again, that has to be assumed before you can do anything. This quantity cannot be observed directly because of the presence of topography, so they must estimate using a model of Earth's gravity within the topographical mass. And that's a quote from Featherstone, WE 6 Southeast Asian Surveyors Congress, from the Use and Abuse of Vertical Deflections, Proclamation 6 Southeast Asian Survey. So, wonderful quote. It's a PDF. We'll throw it in the chat. So that's the answer to reciprocal zenith angles, right? You don't have to worry about any of the answer or how they're doing it. You just have to attack the basis of what they're doing. It's kind of the same answer for every globe argument, honestly. You don't really listen to the nonsense part of the hypothetical. You think about what they're asking, you figure out where they're presupposing and being logically fallacious. You point that out, argument goes away. Fair enough? Super easy. So they said they apply the known method of simultaneous reciprocal vertical angle measurements to derive the refraction coefficient. Sorry, I was muted. Real quick, whenever they say, oh yeah, refraction is a thing, but we'll just do some reciprocal Zenith action and we'll take care of that, cancel it right out. Wrong. There's a study that shows actually that simple measurement of reciprocal Zeniths, when you're trying to do it, line it up, is itself a huge impact on refraction, and it has a wide variance. So this by itself would just lead you to conclude that it's possible this sphericity that you're determining has always been in the margin of error, since
You can't even be sure when is up and down is down and how level your plumb bob is. So when you're trying to do parallel angles, you can't accommodate correct refraction, then your measurement doesn't show sphericity. Simple as that.
And they went out and they took unique parallel observations to test the refraction coefficient along 3 lines of sight with a total of 6 total stations. And they took their fluctuations and amplitudes and went back and forth and took many readings. And they pretty much discovered that their refraction coefficient can vary on a regular day anywhere between -4 and +16. That's a huge amount. This equates to like a ridiculous amount of leeway. So when they say that they apply the standard refraction, the Gaussian refraction coefficient, often suitable to describe refraction effects well above the ground, is definitely not representative for effects of the lower atmosphere, i.e. where everyone does their reciprocal zenith angle measurements. That's where it's not fit. So absolutely hilarious to learn that. Actually, it turns out that when they do this, they have this refraction coefficient that screws up their measurement of what is supposed to be a minute enough measurement to tell us the shape of the world. So this is, where the line really is, and here's where they would see it. Curved. S is bent between 2 endpoints with the Earth radius. And it says it's a little bit between 4 and +2 when it's 1.5 meters height. And when it's looks like when it's right at the ground, it's between -4 and +6. So they went through all of these. This is possible variations of -47 and +20. Literally, this is bouncing all over the place. Essentially, it's doing this, right? All the time. And they're measuring with an optical theodolite or total station. And they're looking, right? And they're taking a measurement. And they say that, oh, this little tick right here, that this where this water is, that's where I measured. And they come back the next day and it's way up there, way down there, way up there, way down there. This little tick measurement right here is way more than enough to denote sphericity when derived backwards through the calculation to get the shape. So this is just one aspect to go through when trying to attacking the reciprocal zenith angle argument. Personally, I like to remember that the radius is derived from applying the coefficient of refraction. So if you're applying refraction in any way, and they have to use it, they have to presuppose the radius, because the radius is included whenever you're using the coefficient of refraction. Let's see here. It looks like, yeah, so here's from the paper. Here's all the coefficients of refraction that they denoted. And they were supposed to use that to counter refraction again. Just saying. Yep. So when they use refraction, they define it as the ratio between the radius of Earth, r, and the radius of the line of sight. Literally have to use the radius of the Earth to have an arc angle, to use geodesic surveying, or to invoke refraction or a refraction index gradient. So if you have a refraction coefficient, you're invoking a radius, right? They have to do that. They said it's based upon a circular arc used to model a regularly curved path of light, i.e. follows Earth's curvature. Would you look at that? And look, the radius of a circular arc used as a mathematical model to approximate a complex path curve of light. So this is exactly where they say this is the domain in which optical geodetic measurements are often carried out. And they said, so this coefficient right here is well known to cause all sorts of fluctuations. And again, that's already on top of the tools themselves having such wonderful built-in features as automatically calculating Earth curve and mean refraction. So if the tool is set to use this coefficient refraction at this rate, which itself is already invoking the radius of Earth, which is then going to match the measurement when they go to compare it to the radius of Earth. Does anybody else see the problem with this? And I think we'd be doing the community a disservice if we didn't go into the basic logical objections to measuring reciprocal zenith angles in the first place and using that to prove or substantiate anything, right? You have factors that are associated with the implication of curvature. You have factors associated with optics, and together they sort of extend and extenuate the curvature attribute. Let me explain, right? So when you have the deflection of the vertical and you're taking into account refraction and say, let's say, the favorite modeling of refraction and the standard index of refraction, and then you have the 7/6R, the extension out of refraction out on the surface of a ball. So what this would do is affect the elevation differences. So here's a manual from, I think this is Mass Highway, how they deal with it, and then it's sort of a well-known disparity. So again, when people on the internet tell you that they know the Earth is curved because of reciprocal zenith angles and measurements within arc seconds, just keep all this background stuff in mind, that how they actually determine it is well worth being questioned and called into the weight here. So it says the two things they know that affect their measurements are atmospheric refraction and Earth curvature. Like I said, the two errors can affect elevation differences and zenith angles in opposite directions, but atmospheric refraction error is approximately 13% of the error for Earth curvature. So they make a negative correction one way, a positive correction the other way, and it's just something that they have to accommodate. But if we want to just take a general stance and poke at the problems that they're kind of introducing by trying to take a method like this, we can take a look right here. So there's like plumb line deflections that are perpendicular to the lumpy geoid terrain, which don't match the topography. That's the general principle when you try to look for a deflection of the vertical, how they don't line up. So that takes away from their claim of measuring spherical excess and measuring reciprocal zenith angles using this, but they also have non-conforming refraction models, downward refraction models that vary, refraction coefficients that change with the time, the season, and the state. So we can look into that just for a second. There's a couple of quotes that we know support what we're trying to explain. Because of the complex process required to calculate an exact value for the refraction coefficient in every surveying task, it has been suggested for simplicity that specific values that approximate the average state of the atmosphere be applied. Such values include global K equals 0.13 for all latitudes and all seasons. The specific value was introduced by Gauss for arc measurements in Hanover in 1823 and has been applied extensively ever since. So again, they're saying that they are familiar with the broad application of 0.13 for all refraction all across the world in every season in every circumstance. Obviously that's not ideal, but it's how they work with the average. Now another quote. On the basis of reciprocal vertical angle measurements near Hanover, Germany, Carl Friedrich Gauss found an average value for the refraction coefficient, approximately plus or minus 0.13. And the value of K is well known to the surveyor as a frequently used standard value of terrestrial refraction. Here's another one where they explain how that causes problems. Empirical modeling of refraction error and trigonometric heightening uses meteorological parameters. Right, so monitoring of the refraction coefficient in the lower atmosphere using a controlled setup of simultaneous reciprocal vertical angle measurements. So they know that essentially with the margin of error you get in spreading out the triangles over a large distance, hiding ocular measurements within, things like refraction and dip angle, they have a huge fudge factor to turn all of their planar surveying data and measurements, which is all they ever take in reality, into this, fantasy geoidal model that has curvature. So they have this fudge factor. We figure it's between 3 and 5%, really, between the plumb line deflection, the difference between the refraction of coefficient, and all the things that apply to vary.
And I mean, I think I'm still muted. Yeah, don't forget, we just watched that. The first paper we showed was the evidence of refraction within the reciprocal zenith angle measurement. So they're applying a coefficient of refraction standardized across all measurements and all times and all circumstances. Don't forget that they're applying it to that wild fluctuation of the usual thing at right about the depth that they're measuring. So it's kind of screwed from the start. I would say anything you measure is due to the wild fluctuation of the atmospheric conditions and thus not sphericity. But let's see, an optical measurement. Just remember that that horizon that we looked at over the water that was frequently changing and fluctuating all throughout the course of one day, just from basic changing atmospheric conditions, right? That's what we're talking about, those fluctuations and variations. Apparently, when they're taking measurements, that's always 0.13 all over the world. See what I mean? So when you only need, tiny arc seconds of variance within some of these observations optically to turn the standard flat surveying data into technically geoidal, geodetic survey data, meaning that the presence of a curve is necessary, there's a lot of wiggle room in their observations, in the application of the measurements, in the calculations, and in the whole process to make it happen, right? So you can see if you were trying to influence this to become a sphere, you have many stages and many opportunities along the way to do so, okay? Know that when I got to flat Earth and I had
my mind made up and I knew all the answers. Not really, but when I got here and they showed me a theodolite and they showed me the distance observations they took and they showed me the disappearance from the bottom up and all the correlations, inside, without telling anyone, I was convinced that they were just like, a devil machine that would just show me the globe. No matter, I couldn't figure out how I could see the globe out of that thing, but couldn't see it anywhere else. And then I looked at like a manual of one of the theodolites given to me by Amish. Man, this thing's awesome. Well, look, for reduction formulae for reflector, this instrument calculates slope distance, horizontal distance, height distance in accordance with the following formula. Earth curvature and mean refraction coefficient K equals 0.13 are taken into account automatically. The calculated horizontal distance relates to the station height, not the reflector height. Well, isn't that cool? It's almost like it already takes into account the globe model. Oh, that's exactly what it does. That's amazing. So again, let's do this. I'm going to read it one more time. This instrument calculates slope distance, horizontal distance, and height distance in accordance with the following formula. Earth curvature and mean refraction coefficient K equals 0.13 are taken into account automatically. The calculated horizontal distance relates to the station height, not to the reflector height. Interesting. I mean, really interesting. Another technical specifications page of a theodolite, and we're looking at range, strong haze, 5 kilometers, strong sunlight, severe heat. So like the entire conditions of the American Arc of the Parallel, they were out there in the clouds and the thousands of mile distances, making these optical observations and then making those determinations based on the model and the plumb model, the plumb bob, which we just went through. Boy, dancing in presuppositions usually. Another one for the XR rangefinder portion of probably a theodolite or a total station. It says the coaxial XR laser makes it possible to measure distances over 170 meters, 560 feet, reflectorless, and over 10 kilometers, 6.2 miles, to one prism. Well, that's a much smaller distance than anyone who uses them to prove the globe model ever uses them. They're intended for much shorter distances than what they're used for. That's pretty crazy. Just another part where they automatically incorporate earth curvature, automatically corrected for line of sight.
Just turn on the earth curve button.
Index,
oh wait, turn it off.
Axis, standing axis tilt, earth curvature, refraction, and circle eccentricity. Yeah, well, you need all that if you're gonna go out and measure the globe with a tool like a theodolite, I guess, right? Man, good to know that I wasn't crazy. That we finally figured out what's wrong with the on the evidentiary pass. This is another paper that has a wonderful diagram of the deflection of the vertical, and we'll take a look at the evaluation of the plumb line curvature effect on the deflection of the vertical. Pretty useful paper, right on point, goes through exactly what we're talking about, and it has his model here, I think. So yeah, I was talking about the terrain, the telluride, the geoid, the quasi-geoid, the ellipsoid, all have different bearings and different alignments. So that's what he's aligning. Again, it's a pretty common issue. It's exactly his gravity vector on the actual and normal potential surfaces. And his deflection of the vertical would involve, let's see how much, if we were to find it. Because it would be a significant portion, a couple arc seconds, which would be enough to confuse a measurement, right?
Can you turn it up a little bit, Shane?
Yeah, I can't really hear anything.
Yes. Wow. And let's continue with the next paper with the same topic. It's the first measurement.
I was just going over papers that go over the deflection to the vertical and marking out how they impact the exact measurements that they're trying to use them with. So it's kind of like a third avenue of attack. If you don't want to attack refraction or the basis of the plumb or how they're determining level, you can just say, well, with the deflection of the vertical, it means that on a geoid you can't actually ever align the plumb without invoking the radius because you don't know the equipotential perpendicular relationship to gravity. So the geoid definitionally requires a perpendicular relationship to gravity. It's weird, I know, as a shape to define that, but it does. So you can't define down in a geoid unless you use the plumb bob. You can't just go down towards the center. But yeah, that's the perfect, I think, place to attack it. But the deflection of the vertical is kind of the way that you can just like that. That's where they can hide any of the measurements. Usually it's greater than the amount they're showing. I think the one that I had for the paper, something like 22 to 24 seconds, but
Of the deflection
depends.
of the vertical in longitude. So this one's a little different. Let's see here. This one is in the 1830s, well after the U.S. Coastal Survey and the other surveys, before Clark ellipsoid of 1866. Besides revealing the actual non-measurement of this presumed deflection, this documents how the globe is a projection onto the celestial sphere in the first place. Intriguing historically context behind the thought and mythology to project a flat world onto a celestial sphere. Essentially, they look at the night sky and they find that the stars are not precisely where they expected, and they given a specific time, and they coordinate references to utilize what that offset would be, where they would be exactly where they would be. So they mathematically corrected the terrestrial measurements to conform to the astronomical coordinates and called it a measurement.
Oh, they got all spheres now: geodal sphere, celestial sphere, longitude sphere. They just have all the alignment of the spheres, and they can make measurements from any portion of any which one. So you don't have your geodal sphere, just look to the sky. Ran out of the sky and go look to your geometric sphere. It's amazing. But this one was sufficient because the first time they did this and they figured out that they could align it, it was disastrous. Let's see.
So this was very dangerous. They determined the longitude differences he had measured, and they combined it to form the offset. So essentially, he did his own offset and corrected it without any other forms of corroboration using the stars. So the solar altitudes were recorded, and the transits were observed, and then they pretty much composed where they were from that. They used the time measurements. They looked for correlations, but they did it. See, the precision of the results is remarkable. An error not greater than 0.025 seconds on the time scale. So by looking at the astronomical correlation, he was able to fix it. And it correlated with later measurements, of course, via the longitude, latitude corrections. Taking a look at the conclusion here, it just goes into exactly what we were talking about. You know, the importance of the deflection of the vertical, and they were so important that they were able to solve the alignment problem without any other corresponding alignment. And they looked at the stars with the transits and were able to tell. So they essentially merged the geodal model with the celestial sphere model. When in doubt, they can use the celestial sphere to offset the geoid. That's essentially what happened. Speaking of coordinate systems and aligning the geodal long lat system to the celestial sphere, there's this National Almanac from 1776 in the Astronomical Ephemeris that actually has an interesting passage about specifically this longitude lat system that after they invented, they actually put out a reward or a contest to see who could try and figure out how to mark your longitude. So they could figure it out in the south to see how it works. So they say, if such method determines, actually, let's start at the beginning. It says, concerning longitude at sea, except thereof as relates to the appointment and authority of a whole bunch of other words and commission to make useful discoveries in navigation and for the better making experiments relating hereto, for the anyone who may discover, or actually says, who fath discover any method or methods for finding the said longitude, be it enacted by authority or forefaith, yada yada yada, for each and every such method as to hit her executors, sums of money heroin after mentioned. That is to say, man, it's a lot of words. I think they offered a reward. Yeah, that if such method determines said longitude to 1 degree of the great circle or 60 geographical miles, the reward of 7,500 pounds. If it determines the fame, and to reward the sum of 10,000 pounds. If it determines the fame to 1/2 of a flayed difference. So it seems to be saying the closer to 1/2 a degree of accuracy you can help me mark the longitude lines in the south, then I'll pay you more. So it seems like that was a great project for them to do. And now that they can align, say, a spherical coordinate system using a theodolite to a celestial coordinate system, also spherical, is extra useful, isn't it? And just so we know what kind of margins we're talking about here, when people try to dismiss, well, you don't have to worry about the deflection of the vertical. No, I already accounted for it. Well, here's about what we're talking about. This is a paper surprise, surprise, studying the amount of deflection of the vertical and the effect on leveling measurements and the distribution geometry. So they can't bullshit their way out of it. Let's just see what they're, and the same problem that we've been going over and over. They try to solve, but then they come up with, actually, the components of the deflection of the vertical at solution A was found to be off about by negative degrees, 0 minutes in 2.490888865 seconds. So, I mean, 2 seconds is good. That's a lot. This one is 4 seconds, 0 degrees, 0 minutes, 4 seconds, 0.2970846. Together, that's, you know, that could throw a measurement. That could throw it from 179 to 80 easily when they needed to. And the other one was registering at off 1 degree, 0 degree, 0 minutes, 25 seconds, 0.08863, yada yada. 25 seconds is a lot. If we were doing our measurements from before, and we had a correction column as we were playing around with, and we decided to put it in and say, let's say, 46 seconds. Let's say if we went from, so let's add 25 seconds and 4 seconds. So just two measurements that didn't make it. Let's say this one was close. 25, 4. Very close. The other one I think was found to be even bigger. They graphed it out based on the ellipsoidal height and the difference. And look, linear response, a linear relationship. And here's some more variances they caught. Literally huge 25-second deflection area. So depending on where you are,
Yeah, they're usually claiming spherical excess within those margins to begin with.
a drastic effect on what you're measuring.
It's like, no, actually, you just don't know how to
Measuring
align your
something really
tool
small,
because you live in a
Yeah,
fantasy
you can
ball.
lie within the measurement. All right. I'm just going to wrap it up real quickly, combine everything, make sure we recap what we did, how we answered each question. So essentially, we're attacking not what they say, but what they're assuming when they say it. So spherical coordinate system, when we're doing the American arc of the parallel, when we're incorporating spherical excess, and we know that they're hiding it in the larger triangles with the adjustments they have to perform to the spherical coordinate system long lat, and to the stars, and to every other coordinate system they can. So they do adjustments all the time to adhere to that model. When we do reciprocal zenith angles, they try to do the same thing. They try to use those measurements and angles to convince us that actually it could only be a sphere. And again, the answer there is to attack the nature of the plumb and the true, relationship to perpendicular. And you'll find that they can't actually figure it out. It's plagued them forever. There's papers and papers written on it. It's called the deflection of the vertical. And once you go into that, and you can understand that actually to get even what they're doing, they have to assume not only the radius, but literally every aspect of the globe model. So as a method to prove the globe, this spherical excess or reciprocal zenith angles is a terrible tool, right? To prove the globe, you have to say, assume that on a globe Earth, plumb is not plumb, down is center. So you have to assume it's relative to the center of mass, and that they can only determine the center of mass as gravity due to axial rotation. Then there's also a gravitational flux. As you presuppose the basic spherical nature, and because you know the exact radius, and then you have to have it down to such a high level of specificity that you're to get the arc length, which is different than it could ever be on a flat plane, because it has to have the radius to be an arc to be plotted. And therefore, geodetic surveying cannot even be attempted or done, let alone completed, without aspects of the globe model, including the radius. So therefore, can never be used to prove the globe model. And don't forget, by the definition of a geoid, that it has to have a plane perpendicular so it can make the measurements to itself. It can't actually determine down to the center of mass, because all of that is nonsense. So those are the arguments. Those are the refutations. Let me know if you think we got anything wrong, and we can improve any aspect along the way. Thanks everyone for hanging in there.
There we go. Finish it out. What do you guys think?
Yeah, that was awesome.
Good stuff.
Word. A lot of nonsense in there, man. A lot of presupposition.
Rui dipped.
Yeah, well, he was hanging around for the longest time, and then he was like, "Yeah, send me a later. I have to go." I was like, "So you could stay for 56 minutes, but not 60?" No, I got it, dude. It's cool. Makes sense.
Respect.
Got to feed them dogs. No, I'm just kidding.
Yeah, I would be interested to hear what he has to say because it's like what you
I can
just laid out is
show
kind of what we all
you.
assumed, but it's like you went through the documentation specifically, found everything that just went through the whole timeline. Really, you know.
Yeah, he
We
was
can see.
messaging me about each aspect as I was bringing it up with his refutation, but I'd already planned for that. So the next
Oh,
step
nice.
was to me refute it. So a couple of times I saw him texting me, and I'm like, "I bet I'm answering that right now, bud. Don't even worry
Nice.
about it."
Nice. Yeah, cool.
So the
Like, so there
radius is
is no
every time they ever say anything about a coefficient of refraction, that inherently has a radius baked into it.
100%. And here's a nice meme to show you exactly how, in case they're unfamiliar with what they're doing, which would absolutely be the case.
Yo, Toby, and depending on the theodolite they're using, it may have the radius baked into the lens, dude.
Or the curvature button turned on to manufacture curvature wherever you look or whatever.
Yeah, so I kind of missed what model theodolite was that?
Yeah, I looked it up. It's legit. But so apparently this is a known thing. Like people have voted, like Jesse knows, and they're like, "No, we just turn it off. You guys are silly," and that's been sufficient. And people.
Well,
didn't
but
think-
I just
like,
was curious. Can you drop that manual? Do you have that PDF?
Yeah. I do, but here it's the model number is listed in the meme in the corner. Like you can see it. That's how I found it. Let me see.
Did you already?
Let me find that one. Yeah, I was showing those, and Rube was like, "That's not what they're using for this experiment." And I was like, "I know. That doesn't mean for that." And I know, dude. I know it's cool. Don't worry about it. I still think it's He's like, "They didn't use theodolites in the arc of the parallel." I'm like, "I said that. I know. I just think it's
those
related."
old helioscopes.
Yeah, dude. 238-mile light flash in the middle of the mountains on a misty fucking morning. Yeah, no, it's definitely a ball. 100%, I believe you. You guys are professionals. I dig the hat.
I love the
When I
Earth curve
seen-
button.
when I seen those colored in pictures of the Arc of the Parallel expedition, man, I don't know how you could think it's flat, man. After that,
Dude, they pre-programmed sphericity, laid down a sphere structure, put in the parts of a sphere, painted it the sphere color, and they were like, "Behold, it's spherical." And we're like, "Oh, crazy! Wow, that's amazing. We proved it." Look at this one, dude. This one specifically incorporates the coefficient of refraction that's the one that they standardized, 0.13. Well, actually, it's not standardized. There's a huge discrepancy. A lot of people use different ones, and one of the main uses 0.14. All of that just adds to the radius projection amount. So if you're including refraction, you're saying that the light in front of me I'm projecting will curve this way, and it matches the curve of the Earth. So when you're doing that in any aspect, you're already presupposing the radius, and you're saying the light will bend to match that. So that's crazy. Why would I let you do that to compare measurements or do anything? You're going to pre-factor in all your globe stuff and then always be backwards compatibly right. That's stupid. Why would I even bother?
So you said also you kind of made a comment in there or something about how they mathematically correct the zenith measurements to match a celestial measurement. Is that correct?
They align to the stars repeatedly, yeah. Yep. And that's
Okay.
because the first time they did that deflection of the vertical, they figured out how, right? They figured that they plugged the holes and they were like, "Oh, we can align it." But what they really did was figure out that it was all already pre-mapped, and they figured out that if this portion of the map is missing, that portion can fill it in because they're equal.
Yeah, and man, it's crazy too because they really assume they're infinite distances, and so they would never when you look at the what's it called, the angles to Polaris that Gleam drew, that linear, that relationship as you go away down in latitude, it would imply a uniform height of the cosmos potentially, right? Or a known height of certain stars, or not a known height, but an observed. Because I don't know if the stars could potentially just be relative positions or in any case, what they don't include in any of their measurements is the essentially the deflection, right? Or the deflection of the vertical on the inverse. We have a deflection of the vertical. You illustrated that really well with the coin being dragged away on the table. But then if the upper plane was the same thing, there'd be the same thing inversely, like a deflection of the vertical of the of the celestial observations.
Well, deflection of the vertical specifically applies to like a plumb bob trying to align on a geoid.
Okay,
Right,
okay,
because-
gotcha. But
yeah,
that's
it's not
still
just like-
but that still invokes the same concept, right? Of like or no, never mind. That's the linear relationship to the geoid. Okay, never mind. Or the
Yeah, dude. So like the
perpendicular
deflection of the
relationship.
vertical, if you think about it, right? If you're on a curve and you have a plumb bob, and you know that it just falls to level, but you don't know which way is down because you're on a curved ball.
Oh, so I
like, you just
misunderstood that
assume
paper then. Can you drop that paper, by the way?
the one that goes over the refraction that they found when doing those measurements for
Or the
reciprocals, or-
deflection of the vertical paper.
Yeah, there's a mini. So I dropped the whole bibliography,
Oh, nice.
and like eight of them are about that specifically. So let's see. Yeah, so determination of the vertical for implications on terrestrial geodetic measurement, evaluation of plumb line curvature and effect on the deflection of the vertical, and the first measurement of the deflection of the vertical according to latitude were particularly helpful. And then there's the calculation of the deflection of the vertical, including offset with GPS.
This is the one I wanted. Cool. The one by Andreas Schrimpf.
Yep. Yeah, so there's a good 11 PDF library. I think I put the list in there, but anyone watching should probably go through it. You should read about how they're convincing you that it's a sphere by doing predetermined calculations on my Earth curve inherently calculating theodolite. Turn that Earth curve button off, Jesse. Dude, I was so surprised. They were like, yeah, we know about that. We argued for a little while, and then everybody forgot. And then we let Jesse present theodolite measurements over and over with predefined Earth curve and dance around. I mean, come on. Who would tolerate that? Did you guys all know that this is how they were doing it? Like, would you have tolerated that if you were like, Jesse, can you make sure that the Earth curve button was off, though? Because otherwise I'm a little suspicious.
So then what was the phrase that I was looking for? I think it's just diffraction is what I was thinking of actually earlier.
Well, the deflection of the vertical means that they can't actually know, like, where they can't actually determine level. That's what I was trying to figure out. To point that out, this is what Whitsitt did in his geodetic survey debate. But he did it in like 3 minutes, real quick, and I missed it like 2 times. But when I finally realized, I was like, oh man, you can't even do anything without presupposing the radius to calculate the amount that the plumb bob will curve, so you can calculate the first angle to anything.
Yo, yeah, by the way, I had a light bulb moment during all that because I'm in the middle of trying to put together this this geodynamo presentation and doing a bunch of research on geodynamo and geology. And there's a problem in their model because there's the thing called the shell theorem, which is the idea that at the center of mass of a planet should actually have the least gravitational force. It should actually be 0 at the very center. So the fact that we have an iron core with the most dense portion of our planet is actually kind of incoherent in the theory of gravity. But we need, when you were talking about all this, it made me realize like they have to have the most dense part be in the middle, because that's the only way that they can actually have gravity make any sense and try to draw any sort of plumb bobs or anything like that.
Yes, down towards the center is inextricably linked to that. And if you don't look into like surveying, you don't ever realize it. Once you finally see it, like you don't even know which way is down. You're on a fantasy ball. You can't even tell which way is down. You have to use the same method that we do. But then you have to like tell us that you could just look down. It's like no. In actuality, you have to determine down the same way we do because it's universal. And then you go back to pretending that it's every which way away from the, you know what I mean?
That's why they have to invoke that insanely pressurized iron core. Wow, yeah, but which is already incoherent.
So they're inventing things to like, manufacture cohesion. But if you look at this picture right here, what it actually shows is the deflection of the vertical, right? They have so many overlapping pseudo, ellipses and horizons that when the geoid height aligns with your ellipsoid height and it doesn't match, you're left with this problem. And that's what the deflection of the vertical is. So Literally, they have the ellipsoid model, the geoid model, and they have this vertical plumb on a sphere, and they can't get a model line up, and that's why they have this huge problem. And then they're telling you that because they know exactly where it is, the difference in those two angles shows that the Earth is a sphere. So, maybe they should back up on the degree of certainty when they say that shit. But there's been a big argument that people haven't really just kind of let people say it. And I think we should crush that shit down now and never even tolerate it. And we'll take back, sky, interferometry, motion. Eventually, there'll be no argument left.
As it should be.
Rock on. Yeah, that was a fun one.
Yeah, you killed it, man. That was fantastic. Should we go ahead and wrap streams up? Does anyone have any other questions or anything? Cool.
Riggs, geocentric? Nobody?
Well, cool then. I'm going to go ahead and stop my stream.
Yep.
Same here, brother.
Short and sweet.
I'll be
Thanks
right
everybody for tuning in. See y'all on Thursday for reading night here at Æther Cosmology. This week we're going to be reading Stephen Crothers talking about LIGO and their gravitational wave detection in preparation for an upcoming presentation about LIGO that we'll be doing probably not next week, but the week after that. Because next week, I believe Alan is going to be giving a presentation about the orders of measurement and abstraction versus first order measurements. But LIGO will be a perfect piggyback off of that because we go from first order measurements to second order abstractions to convolutional neural networks with multiple layers of deep filtering and classification that are essentially not in any way connected to the reality from which they were derived. So in any case,
we
we will be getting into that soon. But yeah,